Good morning, students. In today's class we are going to see what are second order derivatives and how can we find them out. So let's start with second order derivatives. See, normally the first order derivative is represented like this. Okay, and second order derivative means to differentiate the first order derivative again. So if we want to differentiate this derivative with respect to x, then this expression can be written as this. You can read it as d2y by dx square or even d square y by dx square. This can also be represented as y double dash. We can also represent it as y2, 2 is the subscript. Okay, so number of ways of representing second order derivative. Let's take one small example and understand. Suppose dy by dx is equal to sine x. Alright. Then we want to differentiate it with respect to x. So differentiating the left side with respect to x and likewise the right side with respect to x. Like this. So here you notice that the left hand side expression is d2y by dx square, and on the right side the function has variable x and here also is variable x. So we are differentiating with respect to the same variable and hence we get cos x. So first order derivative is sin x and the second order derivative is cos x. Now suppose our function, the first order derivative was suppose sin t. Alright, and we want to differentiate both sides with respect to x. So right side also differentiating with respect to x. So once again here the left hand side is d2y by dx square. Now on the right side you notice that here the function has variable t, but then we are differentiating it with respect to x. So if the variables do not match, then we can consider sin t as a composite function and then differentiate first sin t function, so we get cos t, and then we differentiate t with respect to x. So here you can see if it is a composite function the result is this, but if it is not a composite function the result is the second order derivative is simply cos x. So this is how you have to differentiate between the variable and the kind of function. So next, let us start here with exercise 5.7 from the NCERT textbook. In this exercise, we are going to find out second order derivatives with respect to x only. So the first question that we are going to try out is question number 3. Third question, a function is given as x cos x. So let us call this function y. So finding out the first order derivative using the product rule. So let's write down the product rule. X into derivative of cos x plus derivative of x into cos x. So here x and derivative of cos function is minus sin x. Derivative of x is 1. So this is the first order derivative. Now moving on to the next step where we find out the second order derivative. So we have differentiated the left hand side with respect to x and we obtain d2y by dx square. On the right side we are going to differentiate the first term. So I'm taking here a minus sign common. So differentiating x sin x with respect to x and then differentiating the second term with respect to x. The second term is cos x. Minus sign common. Here again we are going to use the product rule. So here x into derivative of sin x plus derivative of x into sin x. Okay, first derivative found. Then over here derivative of the cos function is minus sin x. Now simplifying it further, derivative of sin x is cos x. So x cos x plus derivative of x is 1. So the second term is sin x and the next term is minus sin x. Opening the brackets and taking finally minus sign common, we get here minus x cos x plus 2 sin x. So this is how the second order derivative has been obtained. So next question we'll try out is question number 6. Sixth question is e to the power x sine 5x. This function is y. So finding the first order derivative with respect to x using product rule. So e to the power x into derivative of sine 5x plus derivative of exponential function into sine 5x. This is equal to e to the power x. Now here this is a composite function, right? So derivative of the sine function is cos 5x and then derivative of 5x is 5 plus derivative of exponential function is e to the power x into sine 5x. So we get here 5 times exponential function into cos function plus exponential function into sine function. Now there are two terms here. So here let's take e to the power x common. So 5 cos 5x plus sine 5x. This is the first order derivative obtained. Now second order derivative. You can see here on the left side we get d2y by dx square. On the right side the function is a variable, has a variable x, so we can write down the product rule here. Exponential function into derivative of the function in the brackets plus derivative of exponential function into 5 cos 5x plus sine 5x. So here 5 is a constant, derivative, this is a composite function, so derivative would be minus sine 5x, differentiating the angle we get 5. Then sine 5x is also a composite function, so differentiating sine function we get this, and then multiplying with the derivative of the angle. And then in the second term, this is the derivative of exponential function, and in the bracket the function is 5 cos 5x plus sine 5x. So in all these terms, if we take e to the power x common, then we have minus 25 sine 5x plus 5 cos 5x. From the next bracket we get 5 cos 5x and sine 5x. So once again, still more simplification can be done, and writing up the positive term first. So that is 10 cos 5x, and then the sine terms, which is minus 24 sine 5x. So the next question that we'll try out is question number 7. Question 7 is given as, we call the function y. So y is equal to e to the power 6x into cos 3x. So dy by dx, again using product rule. So e to the power 6x into derivative of cos 3x plus derivative of exponential function into cos 3x. So e to the power 6x, this is a composite function, so the derivative would be minus sine 3x multiplied by derivative of angle, plus this in the second term the exponential function is an composite function, so we get e to the power 6x multiplied by the derivative of the power into cos 3x. So here we are taking 3 times e to the power 6x common, so we get minus sine 3x plus 2 cos 3x. First order derivative obtained. Then second order derivative, d2y by dx square is equal to 3 e to the power 6x derivative of, once again we are using the product rule, so derivative of the term in the brackets, this plus 3 times e to the power 6x into derivative of the exponential function into minus sine 3x plus 2 cos 3x. So over here what do we get? 3 e to the power 6x. Now both the terms inside the bracket are composite functions, so differentiating sine function, we get this multiplying by derivative of angle, plus 2 times derivative of the cos function is minus sine 3x multiplied by the derivative of angle, which is 3, plus 3 is a constant, so 3 is multiplied by derivative of exponential function, and the derivative of exponential function is this into 6 multiplied by the function in the bracket. So once again what we can take here is 3 e to the power 6x common. This is common, okay? So 3 e to the power 6x common, and This is minus 3 cos 3x minus 6 sine 3x. We could have taken a 3 also common. Okay, we'll do it in the next step. So minus 6 sine 3x plus 12 cos 3x. So simplifying like terms, so cos terms gives us 9 cos 3x and the sine term gives us minus 12 sine 3x. So let's take one more 3 common. So we have here 9 e to the power 6x multiplied by 3 times cos 3x minus 4 times sine 3x. The next question, let us try question number 9. Y is equal to log x. So on the right side we have a composite function. Okay, so differentiating with respect to x, differentiating this log function, we get 1 upon log x. Then differentiating this log function, we get 1 upon x, and differentiating x, we get 1. So our final result is 1 upon x log x. Now second order derivative, quotient rule. So x log x multiplied by derivative of 1 minus 1 into derivative of x log x upon square of x log x. So here this is a constant, so its derivative is 0, so first term is 0 minus, here is derivative. So now derivative of x log x, so that means once again we are going to use here product rule. So x into derivative of log x plus derivative of x into log x upon square of x log x. So this gives us x into 1 by x plus log x upon x log x whole square. So what we are getting here is the second order derivative is minus 1 plus log x upon x log x whole square. So next let's try out here question number 12. Okay, 12th question, there is an equation given. Y is equal to cos inverse x, and then we have to find out here the second order derivative of y with respect to x in terms of y alone. So this is the given equation. Let's write it down as cos y is equal to x, and now let us differentiate left side with respect to x. So I'll just write down this step here. We are differentiating the left side with respect to x as well as the right side with respect to x. Now here you can see variable is y and here the variable is x. Variables do not match, so we can consider this function as a composite function. Hence, differentiating cos function, we get minus sine y, derivative of y, dy by dx, which is equal to 1. So finally we are getting the derivative dy by dx as minus cosec y. So you can see here first order derivative obtained in terms of y. Next, second order derivative. So second order derivative, so we have differentiated left side with respect to x, and on the right side minus sign taken outside, so derivative of cosec y with respect to x. So here once again you can see these variables do not match, so that means the function on the right side is a composite function. So derivative of the cosec function is minus cosec y cot y, and then differentiating y with respect to x. So here minus minus becomes plus and we get cosec y cot y, and the first order derivative from here is minus cosec y. So our final second order derivative is minus cosec square y into cot y. This is second order derivative. So you can see here the second order derivative has only variable y. Okay, next we are going to try out question number 13. So 13th question. Y is 3 cos log x plus 4 sin log x, and then we have to show that x square y2 plus x y1 plus y is 0. So you must have identified this is first order derivative, this is second order derivative. Okay, so let's find out here the first order derivative. So 3 times derivative of this function, which is a composite function. So differentiating cos function, we get minus sine log x. Then differentiating the log function, we get 1 by x. Likewise on the right hand side, 4 is constant. Here again we have a composite function, so differentiating sine function we get cos log x, and differentiating log function we get this. So you notice here that there is this x in the denominator. So we are shifting this x to the left hand side, x y1, which is equal to minus 3 sine log x plus 4 cos log x. So here this one is an important step. Here you have to understand that whenever we have an x or any term in the denominator, in the very next term it should be taken to the left hand side. The reason being simple, if we do not shift x, then we will have to do quotient rule here. If we shift x here, then we will be using product rule, and I believe using product rule is simpler than using quotient rule. That's the idea. If we shift the terms, the second advantage is that the number of steps also reduce and the question can be solved in a simpler way. So now here we are going to use product rule here. So x into derivative of y1 plus derivative of x into y1. Moving on to the right hand side, these are again composite functions. So 3 cos log x into 1 upon x plus 4 into minus sine log x into 1 upon x. So here again you see that we have got an x here. This again we are going to shift to the left hand side. So the first term here becomes x square y2. Derivative of x is 1. Since we are multiplying it by 1, so we get this kind of a term. And on the right side it is minus 3 if we take minus sign common. So minus 3 minus sign common, so 3 cos log x plus 4 sine log x. And now you can see that this right hand side is same as the function y. So it is x square y2 plus x y1 equal to minus y, which means that x y2 plus x y1 plus y is 0. This is same as we were asked to show here in the question. Hence the result is shown. So you can see here, simply by shifting an x term here, the number of steps are simpler. Number of steps reduce and the steps are also simpler, and we can easily get the right result. If we are not doing this step and from the second step only we differentiate using quotient rule, we will still get the result, but the number of steps would be more. So next we'll try out another important question, that is question number 14. If y is equal to a e to the power mx plus b e to the power nx, then again show that d2y by dx square minus m plus n dy by dx plus mny is 0. So first order derivative, a is constant multiplied by derivative of this exponential function. Derivative is this, because it's a composite function, we multiply by the derivative of the power also. Likewise for the second term, exponential function multiplied by n. So that's first order derivative, there is no term in the denominator. Then second order derivative. So am is a constant. Once again differentiating the exponential function, we get this. In the next term, bn is constant, so constant multiplied by the exponent derivative of exponential function, which is this. So the second order derivative that we are getting here is am square e to the power mx plus bn square e to the power nx. So first order, second order derivatives obtained. So now we'll go back to the equation, the left hand side. Second order derivative minus m plus n times first order derivative plus mn times y. This is what we'll find out. So let's put in all the values here. So we are getting here am square e to the power mx plus bn square e to the power nx minus m plus n times the first order derivative, which is am e to the power mx plus bn e to the power nx plus mn times y, which is this. Now simple expressions, calculation work here. am square e to the power mx plus bn square e to the power nx, and now multiplying with m first, so we get minus am square e to the power mx minus bmn e to the power nx. Next we'll multiply by n minus amn e to the power mx minus bmn e to the power nx, and then the last two terms amn e to the power mx plus bmn e to the power mx. So now you can see here certain terms cancel out, so this term will cancel with this term. Bn square, where is bn square? Oh, this one, this is n square. So here when we are multiplying by n, so this becomes bn square. Alright, so here you can see bn square can be cancelled with this term, and minus bmn cancels with this, and the last term that is left is also cancelled. So finally what do we get here? We get a 0 which is equal to the right hand side. So hence the result has been shown. So you can see the difference between this question and the previous question. In this question we found out the derivatives and then we have substituted them in the left hand side of the required equation, whereas in the previous question we shifted the terms and hence automatically we were getting that condition given in the question. The next question that we will try out is question number 16. We are given e to the power y x plus 1 is 1, and show that the second order derivative is square of the first order derivative. There are a number of ways of doing it. So one of the methods can be to take log on both sides. See, you can directly differentiate also. First method you can directly differentiate. Second method you can take this x plus 1 term to the right hand side and then differentiate. So I am using a method where I am taking log on both sides. So we get here log e to the power y x plus 1 is equal to log 1. So using properties of log, it is log e to the power y plus log x plus 1, which is equal to 0. This can be written as y log e equal to minus log x plus 1, and we know log e is 1. So finally we are getting y is equal to minus log x plus 1. So therefore the first order derivative is minus 1 upon x plus 1. Okay, now the second order derivative. y2. So here let us take the quotient rule. So x plus 1 into derivative of minus 1 minus 1 into x plus 1 derivative upon square of denominator. So first term is 0, so we get here plus, this is plus 1, and derivative of x plus 1 is 1, and the denominator is this. This can be written as square of this expression, which means it is square of the first order derivative. So therefore we have got here that second order derivative is square of first order derivative. The last question from the exercise that we'll try out is question number 17. Y is equal to square of tan inverse x, and show that x square plus 1 whole square y2 plus 2x x square plus 1 y1 is equal to 2. So first order derivative, this is a composite function. So on differentiating, we'll get 2 tan inverse x. Then differentiating tan inverse x, we get 1 upon 1 plus x square. So first order derivative found. Now here, because there is a denominator 1 plus x square, so it would be convenient if we shift this term to the left hand side like this. So the question can be solved in a simplified manner. Now let us differentiate the left hand side. So using product rule, derivative of 1 plus x square into y1 plus 1 plus x square into derivative of y1 on the right side, 2 into derivative of tan inverse x. So what do we get here? 2x into y1 plus 1 plus x square into y2 on the right side, 2 upon 1 plus x square. So this term you can again shift here. So I'm writing the second term first. So we'll get here 1 plus x square whole square y2 plus, now the next term, 2x into 1 plus x square y1, and on the right side 2. So this is the same result that we had to show here. So the result is this way shown, and you can once again understand here that because of this shifting of this term to the left hand side, the number of steps reduced and the solving part was also simpler.